we'll test you on. All right, so this will be chapter 9, part 3. I'm picking up with for more practice 9.2, which is on slide 40. No, that's 24. Slide 24. I will write it just for those of you that maybe didn't get my email for yesterday. You will need your calculator most every day to make sure to bring it with you. All right, so this says that a 55-gram aluminum block initially at 27.5 degrees Celsius absorbs 725 joules of heat. What is the final temperature? They did not give us the specific heat of aluminum because they assumed we could look it up. So let's add that. The only equation that we've gone over so far that has to do with heat is my Q equals MCAT. Where M is mass, C is specific heat, delta T is the change in temperature. So I'm going to rewrite this where we show what the change in temperature actually is. The change in anything is always final minus initial. Okay? So in this particular problem, we're looking for TF, or the final temperature. That's what we want to find. We can set this to be our X, if you'd like. Okay, then we're just going to plug in everything else that we're given. It says that this aluminum block absorbs 725 grams of heat. So would that be positive or negative? Positive, because it's absorbing. It's taking in. Okay, so that's my Q. My mass is 55 grams. Specific heat was given, or I gave it to you. And then I don't know my TF, so I'll just put X, minus my TI, which I do know, not the wrapper. Okay, so now it should just look like an algebra problem. We just need to simplify everything down and solve for X. Okay? So I'm going to start that by multiplying these two numbers together. 55 times 0.903. I got 49.665. The gram will cancel and I'll be left with just joule over degrees Celsius. Okay, now from here, I can do one of two things. I could distribute this 49.665 to both of these terms, or I could just divide both sides by 49.665. So that cancels. I'm going to do that. I get 14.597 degrees Celsius. These two joules cancel, and because this degrees C is in the bottom of the bottom, it moves to the top. And then all I have left over here is X minus 27.5 degrees Celsius. Now all I need to do is move the 27.5 to the other side. So to get it there, I'm going to add it to both sides. So it cancels there. And my final answer, I'm going to put 3 sig figs as 42.1 degrees Celsius. Questions? Okay. All right, so this is simply finding the heat, or one of these other terms, of just a system, basically. I need to erase this right here. I'll leave that right now. All right, so we've talked earlier in this chapter that the change in energy of my universe is always zero. It's constant. Okay, I can't create or destroy energy. So that means that the energy of my system is always equal in magnitude to the energy of my surroundings. It's just opposite sign. It's whatever one needs, the other one gives, and vice versa. Well, I could do the same thing with just heat energy. Okay, so I could do Q of my system is the same as a negative Q of my surroundings. Then for each of those Q, I could plug in mass, specific heat, change in temperature. So that's what we're going to do. So that is what we're going to do. Can I erase this? Yeah. All right, so look at this example. This is not in your PowerPoint. We're going to go back to your PowerPoint after we do this example. This example says a sheet of gold weighs 10 grams and is at a temperature of 18 degrees Celsius. It is placed flat on a sheet of iron weighing 20 degrees and at a temperature of 55.6 degrees Celsius. What is the final temp of the combined metals? In other words, what is the temperature when these two metals reach thermal equilibrium? I'm gonna write that word over here. Then it goes on to say, assume no heat is lost to the surroundings. In other words, anytime you see this, what it's saying is that one metal is your system, the other is the surroundings. Those are the two, that's the universe you're focused in. You're not worried about anything else. So heat always flows from hot to cold, okay? When you put two objects together and they're at different temperatures, the heat will flow to the colder object until both objects reach the same temperature, which is called thermal equilibrium, okay? So that is what we are looking for here, is my final temperature of these two objects. So basically, I've just multiplied by my problem by 2, because we're going to do Q of my gold equals negative Q of my iron. Well, I could plug in mass of gold, specific heat of gold, delta T, which we're going to do final minus initial, equals, don't forget your negative. That negative applies to that whole side. So mass of iron, specific heat of iron. Then again, delta T written out. It does not matter which side you put your negative, it always works out. It works itself out. Okay, so this is my equation that I'm going to use. I need to plug everything I know into this equation, and we're going to solve for the final temperature again, but this time we have it in 2 different places, okay? All right, so let's start plugging in. 10 grams for my gold. The specific heat of gold, which I gave you down there at the bottom. We don't know TF. So do y'all want to leave it as TF or you want to write X? Okay. Well, I'll put X, y'all write TF if you want to. Minus the initial temperature of the gold, which was 18. And the other side, I have my negative. I'm not going to distribute that just yet. I need the mass of iron. Then the specific heat, then again TF, I'm just substituting in X. TI of the iron was 55.6. So we're going to start simplifying both sides down. Just like we did in the previous example, we just have to do it to both sides now. So the first thing I always do is I multiply my mass and my specific heat. And I do that on both sides. So I'm going to go ahead and do that. Around, cancel that. Okay, so that's what I'm left with. Now, here is where you could choose which way you want to go. What I normally do here is I distribute this that I just found to both of my temperature terms. So to my X and to my TI. I do that on both sides. So this becomes 1.29 joules X minus I'm also distributing my negative on the right side. I also canceled units as I went along. So far, so good. Okay, now the next part is just to put your like terms on the same side. So I am going to add 8.88 to both sides because it's my X term. I'm going to put my two X terms together. I'm going to add 23.22 joules to both sides because it's my non-X term. Okay, so on the left side, I get 10.17 joule per degree Celsius times X equals 516.948 joules. Now all I need to do is divide both sides by the 10.17. When I do that, I get my X to be 50.8 joules. Nope, not joules. Yeah, degree C. Any questions? See how I distributed everything, how I got those numbers, how I moved things around from side to side. Okay, I'm gonna go ahead and erase this part. We're gonna do one more. The next problem we'll do is actually in your PowerPoint. I think it's 9.3. Yeah, 9.3. Right, so there's what the problem reads. I'll read it aloud. And so it says a 32.5 gram cube of aluminum, initially at 45.8 degrees Celsius, is submerged into 105.3 grams of water at 15.4 degrees Celsius. What is the final temperature of both substances at thermal equilibrium? It also says in the problem, but I was being lazy, assume that the aluminum and the water are thermally isolated from everything else. So in other words, you can use this equation. Q of aluminum equals negative Q of water. Okay, so exactly what I just did over here, this time I'm just talking about aluminum and water. I'm going to give you a few minutes to get it set up. And I'll start working. right, I'm gonna go ahead and start working it out over here. But if you're not done, just keep working. That way you can check yourself when you're done. Space. $17.3 is your answer. Did skip a step. I just skipped writing it. So when I multiplied these two terms together, I went ahead and distributed to my TF and the 45.8. So that's where I got that number. I did the same thing over here. Multiplied them together, went ahead and distributed to both temperature terms and distributed my negative. And when I got there, 17.3. A few people in my other class said that they didn't quite get the numbers I did on this side of the equation or something, but they still ended up with 17.3. So I don't really know what we're doing differently. But as long as you get the right answer and your algebra follows math rules, you should be fine. Any questions? Okay, so for Wednesday, I want you to try for practice 9.3, I believe It's on slide 28. It's like what we've been doing here. This time you're not looking for the final temperature, so it should be a lot easier. A few things about lab. If your lab instructor didn't pass out experiment for this week, it is in the bin outside my door. If you are in Tuesday's lab, I have not recorded the pre-lab video yet. I'm doing it this afternoon, and as soon as I do it, I will email y'all since y'all do have lab tomorrow. This is a very, very tedious and lengthy lab, so please come prepared, have some idea of what's going on.
You said it's probably going to take the whole time, right?
Yes, it will probably take all 3 hours. Y'all have a good week. I will see y'all on Wednesday.
Like,